Limit of a function, part 1. So when we see this mess of symbols here, the way we say this is the limit, so that's what this lim means, of f of x, so whatever is to the right of that lim, that lim, as x approaches a, so that's that little piece down here below the lim, is L. So the limit of f of x as x approaches a is L. And when we're looking at this limit, we're looking at what a function value is approaching as x approaches a. And that function value is the output, which is often that f of x or y. When evaluating limits, we're concerned with whether or not the limit exists, and if it does exist, what that limit actually is. So if we take a look at this first one, we have the limit as x approaches 0 of the square root of x. Well, we don't really know what's going on the left side of our function, but on the right side, as our x value gets closer and closer to 0, our output also gets closer and closer to 0. In fact, this point 0, 0, and that input 0 is right on the edge, the boundary of the domain of the square root of x. So the function doesn't exist to the left of 0. But as we get closer and closer to 0, so as x approaches 0, it appears that f of x is also approaching 0. Now let's take a look at the limit as x approaches 1 of the square root of x. So that means we're looking as our x values get closer and closer to 1. Well, as our x values get closer and closer to 1, it seems like our outputs are also getting closer and closer to this 1. So the limit as x approaches 1 of the square root of x is 1. Now let's take a look at the limit as x approaches negative 2 of the square root of x. Well, as x approaches negative 2, we're no longer within the domain of our function. And this is one of the first examples of where a limit does not exist. When a limit does not exist, we like to abbreviate that to D and E. So the limit as x approaches negative 2 of the square root of x does not exist. Although f of a sometimes has the same value as the limit as x approaches a of f of x, like in the previous examples, this is not always true. So if we're looking at this function here, as we're approaching a, the limit is approaching whatever output is at this hole here. But the actual output of our function is at this closed circle here. So although our limit is approaching whatever this value is, f of a doesn't actually have the same value. Rather than looking at the limit overall, sometimes we like to break our limits up into two pieces. So we can look at the right-hand limit, which we can see by having the limit as x approaches a from the right, where you have a little plus sign to the upper right of whatever a you have. And this is the limit of f of x as x approaches a from the right. And you want to be careful here, because as you're approaching from the right, you're moving to the left. So you start from numbers that are larger than a, and you move towards a when you see that little plus sign. We also have a left-hand limit. So the limit of f of x as x approaches a from the left. And this is denoted by having this little minus sign to the upper right of our a value. You want to be careful that you're not mistaking negative numbers and this notation for approaching from the left. So we're starting with numbers that are smaller than a, and then we're moving towards a. You want to be careful because a left-hand limit starts at your left hand and moves to the right. When your right and left-hand limits are equal, that means that your limit exists. And this little double-barred arrow means implies, if you haven't seen it before. I like to think of this as two people attempting to high five and they successfully high five. They are going towards the same place. But if your right and left hand limits are not equal, that means that the overall limit does not exist. So you can have a left limit that exists and a right limit that exists, but if they're not the same value, that means that the overall limit, so without that little minus sign or little plus sign, does not exist. It's kind of like, it looks like maybe they might high five, but they're not actually going to the same place. Let's take a look at a couple more examples that are graphical. So we're going to start with the limit as x approaches 2 from the right of f of x. Sometimes I find it helpful to put a little plus sign over here and a little minus sign over here, or even draw like little arrows with my plus and minus signs in the beginning, just when I'm getting used to what it means to have a left-hand limit and a right-hand limit. So I'm looking at the limit as x approaches 2 from the right. So that means I'm approaching this x is equal to 2. And for my right-hand limit, I'm starting from the right. So I'm starting over here, tracing my function. What is it doing? It's approaching 1. So the limit as x approaches 2 from the right of f of x is equal to 1. Now let's see what happens as we approach from the left. So we're starting on the left-hand side, tracing our function as x gets closer and closer to 2. It seems like our output is getting closer and closer to 3. Now, if I look at this, my right-hand limit is approaching 1. My left-hand limit is approaching 3. Since my left and right hand limits are not equal, that means that my overall limit does not exist. I can also consider what f of 2 is. So when my input is 2, what is my actual output? Well, it's either 1 or it's 3. When you have a case like this, you want to make sure that you're looking at that closed circle. So f of 2 is equal to 3. And now we can take a look at the limit as x approaches 4 from the right of f of x. So I'm looking at what happens as x approaches 4. We'll start with our right-hand limit. So I trace my function. What's happening as x gets closer to 4? Well, my output is approaching 4. Now let's take a look at my left-hand limit. So tracing my function from the left, whoop, bit of a jump here, tracing, I get closer and closer to 4. from my output as my input gets closer and closer to 4 from the left. Now, since my left and right hand limits are equal, that means that my overall limit as x approaches 4 of f of x is also 4. Now let's look at f of 4. So when my input is 4, what is my output? Well, this one's a little different. All I have is this open circle. I don't have any closed circles. That means that this function has not defined a value for the output when the input is 4. So we can either say that this is undefined, or sometimes we just say that it does not exist. So for the limit, we always say this dne if it doesn't exist, but if the function output is undefined, undefined is probably a better word for it, but sometimes we also say dne when we're working with limits. And then we'll take a look at one last one. Not sure why they thought that I was spelled incorrectly, perhaps because it's lowercase. So we have the limit as x approaches 3. So this is just our overall limit, which means we need to look at both our left and right hand limits. So we're looking as x approaches 3. Let's see. As we approach 3 from the right, it seems like our output's getting closer to 2. As we approach 3 from the left, a bit of a jump, it seems our output is also approaching 2. So the limit as x approaches 3 is 2. Now we'll take a look at the limit as x approaches 0. So starting from the right, as our x gets closer to 0, it looks like we're getting somewhere a little more than 3. And then as we're approaching from the left, we're also getting that something that's a little bit more than 3. So I'd say that's probably about a 3.2. If this were like a test or something, I'd probably accept anything between the 3.1 and 3.3 range. It's something that is definitely less than 3.5 and definitely more than 3. Okay, next up we have the limit as x approaches -2. Well, let's see. This is -1 and this is -2. And we have to remember that the limits exist at the ends or boundaries of our domain. So as we look at this function, we can't do our left-hand limit, but we can still do our right-hand limit. So if we look at where our output is approaching, it's approaching about 1.9. And then again, if we look at the limit as x approaches 6, that 6 is right on the boundary of our domain. So the limit exists, but in this case we can only find our left-hand limit. So as we trace our function, getting closer and closer to 6, our output seems to be getting closer and closer to, in this case, let's see, also about a 1.9. Remembering that limits exist at our endpoints or boundaries of our domains. Now let's take a look at another function. So we'll start by looking at the limit as x approaches -3 from the right of f of x. So we're approaching this -3, and we're approaching first from the right. So we'll go through here, go through whatever oscillating mess this is, continuing to trace, have a bit of a jump, And then from the right, it appears that we are approaching 4. And then we can trace our function in order to find the limit as x approaches -3 from the left of f of x. So starting from the left and tracing our function, as x approaches -3, it seems that f of x is approaching 4. Since our left and right limits are equal, the overall limit as x approaches -3 of f of x, so just the limit, is 4. Now we'll take a look at the limit as x approaches 0 from the right. Let's take a look at this. As we're approaching, the function does crazy things, oscillating, and then we're back to here. And it seems as we approach from the right, our function value is approaching -1. Then we have the limit as x approaches 0 from the left. So we'll trace our function. And it seems that as we approach from the left, our function value is approaching 1. So here our left and right limits are not equal. So the limit as x approaches 0 of f of x does not exist. Let's look at the same function, but a couple different limits. So we have the limit as x approaches 2 of f of x, which means we need to take a look at the right hand and left hand limits, as our x value is getting closer and closer to 2. So starting with our right hand limit, as x is getting closer and closer to 2, it seems like our output is also getting closer to 2. And then with our left hand limit, looking at the outputs of our function, as our inputs get closer and closer to 2, it seems like our outputs from the left are also getting closer to 2. So since our left and right hand limits are both 2, our overall limit is 2. Now we'll take a look at the limit as x approaches 5 from the right of f of x. So now we're looking at the limit as x approaches 5. And I think I might have said left, but I meant right. So the limit as x approaches 5 from the right of f of x. So as we start from the right and get closer to 5 for our input, it appears that our output is getting closer and closer to 3. And now we want to take a look at the limit as x approaches 5 from the left of f of x. So we start on our left-hand side, trace our function, look at what's happening to y as x is getting closer and closer to 5, and it was good until we got to this rapidly oscillating mess. When you have a function that is rapidly oscillating, so that's right here where it just looks like a vertical bar, that means that our limit does not exist. We can't tell what's happening. We know it's going up and up and down and up and down and up and down and up and down and up and down, but we're not quite sure what it's approaching. It seems like maybe it's approaching this 3, but it's very possible that we actually have some sort of gap here. So when you have that rapidly oscillating piece of a function, the limit does not exist. And since one of our limits does not exist, in this case the left-hand limit, that means that our overall limit, so the limit as x approaches 5 of f of x, also does not exist. Next up, we have the limit as x approaches -4. So we're looking at the overall limit as x approaches -4. So we'll start with our right-hand limit. As x is getting closer and closer to -4, what is happening to our output, y? And it seems like our output is probably approaching 3. So that's our right-hand limit. Now let's take a look at our left-hand limit. As x approaches -4 from the left, it appears that y is approaching 3. And since our left and right-hand limits are equivalent, our overall limit as x approaches -4 is also equal to 3. And then the last limit of this example, but not this video, is the limit as x approaches 9 from the left. You want to be careful that you don't accidentally read this as the limit as x approaches -9. This is the limit as x approaches 9 from the left. So we'll start on our left-hand side and trace our function. And as our x value gets closer and closer to 9, it appears that our y value is getting closer and closer to 3. So the limit as x approaches 9 from the left of f of x is equal to 3. Okay, now we're going to look at infinite limits. We'll start with the limit as x approaches -7 from the right. So we're approaching -7, and we're going to start with our right-hand limit. So as we trace our function from the right, it looks like as we get closer and closer to -7, well, there's a vertical asymptote at -7. And as I look at this piece here, it looks like from the right, I'm approaching -infinity. Because as I get closer and closer to -7 from the right, my y values are getting more and more and more negative. Now let's look at the limit as x approaches -7 from the left. So I'm still approaching -7, but now I'll start on the right side. And again, I'm hitting this vertical asymptote. And this piece of my function here is heading towards -infinity. Since my left and right hand limits are both equal to -infinity or approaching -infinity, that means that the limit as x approaches -7 is -infinity. So let's take a look at the limit as x approaches -3. If I look at the limit as x approaches -3, if I'm looking at my function starting with my right-hand side, as my x gets closer and closer to -3, my output keeps on increasing. I have this vertical asymptote again at -3, but this time my outputs are approaching positive infinity. I don't know if I forgot to write my -infinity or if it disappeared. Okay, and then again, looking at a left-hand limit, tracing my function as x gets closer and closer to -3, well, there's this vertical asymptote, and my function output is getting bigger and bigger and bigger. It is approaching infinity. Since my left and right-hand limits, as x approaches -3, are both approaching positive infinity, the limit as x approaches -3 of f of x is also approaching infinity. Let's take a look at a couple more of these. So now we'll look at the limit as x approaches 0 of f of x. So as we're approaching 0, well, again, we have this vertical asymptote. As we look from the right, it seems that this piece is approaching positive infinity. As we look from the left, it seems we're approaching positive infinity. So my overall limit is positive infinity. Now we'll look at the limit as x approaches 6 from the right. So the limit as x approaches 6 from the right. So starting with that right-hand side, I again have an asymptote, and from the right, I'm approaching positive infinity. Now I have the limit as x approaches 6 from the left, and as I look at my function and I get closer and closer to 6 for my input, my output, I hit this vertical asymptote, and this side seems to be approaching negative infinity. Since my left and right hand limits are not equivalent, the limit as x approaches 6 of f of x does not exist. My function is heading in opposite directions. Now we have the limit as x approaches infinity of f of x. So that means as x is getting closer and closer, but never can actually reach infinity, what is happening to my outputs? So as I'm going in that direction towards infinity, what is happening to my outputs? Well, let's see. What I like to do is, if it's a little unclear, to try to extend my graph. So when I look at this piece of my function, to me it seems like this is very similar to an exponential curve. So this piece probably is approaching 0. There's some sort of horizontal asymptote there. It's getting closer and closer to 0, but never actually reaching it. But nonetheless, is approaching 0. So the limit as x approaches infinity of my function is 0. And now we'll take a look at the limit as x approaches negative infinity. So as we head over to the left to negative infinity, what on earth is happening to our outputs? Well, when I look at this looks kind of like the mirrored square root function. So it looks like, although it's probably slowing down, it continues to increase. So that means that the limit as x approaches negative infinity of f of x is positive infinity, because my outputs, my y values, are going to keep on increasing. Rather slowly, but they'll keep increasing nonetheless. So we've looked at how to evaluate limits graphically, so looking at a graph of a function, but we can also evaluate a limit numerically. So just like we were approximating the slope of a tangent line before, we can also approximate the value of a function and look at these limits. Just rather than looking at the slope, we'll look at the output. So here we have the limit as x approaches 5 of the function x squared minus 5x all over x squared minus 25. So we're looking as x approaches 5. As x approaches 5 from the right, so starting with numbers that are larger than 5, and then getting closer and closer to 5, it seems like our outputs are getting closer and closer to 5/10, or 0.5. And then as we look as x approaches 5 from the left, so starting with numbers that are smaller than 5, and then getting closer to 5, our outputs are again getting closer and closer to 0.5. So our overall limit, since our left and right hand limits are equal, is 0.5. Now, if the table's already provided for you, this isn't too bad to calculate. But if you had to input all of these different x's into this rather complicated or tedious looking function to get all of these outputs, that would not be terribly fun. It'd be very time consuming, especially if you didn't have a calculator or Excel. In the future, rather than using tables or graphs, sometimes we're going to take a look at how to find limits algebraically. So we notice that sometimes when you substitute values in, you try to find like f of a, that'll give you the limit. So, well, let's try that out. So we have the limit as x approaches 5 of this function. Well, let's see what happens. Well, when I do this, what is, as x approaches 5, wow, that was a very ugly arrow. Well, that's kind of like inputting 5 into our function. So, well, what is our function approaching? Well, we have 25 over 25, so that's my x squared and my 5 times 5. And then I have another 5 squared minus 25. Oh no! It's another 0 over 0. So I guess that's probably why we were taking a numerical approach for this. But later on, one of the things that we'll be doing a lot is looking at this algebraically. So how to find this limit algebraically. And this is in section 2.3. So this is just a quick preview that you don't have to look at if you don't want to. So we have the limit as x approaches 5 of, well, we have, this can be factored. So x squared minus 5x, we have a common factor of x that we can factor out. So we have x times the quantity of x minus 5. And if we look at x squared minus 25, that's a difference of squares. So that can be factored to the quantity x plus 5 times the quantity x minus 5. And now when we see this, these x minus 5s will divide out. So we have that this is equal to the limit as x approaches 5 of x over x plus 5. And now when we try to see what our output is when our input is 5, we end up with 5 over 5 plus 5, which is equal to 5 over 10, which is that very familiar 5/10 from before. So sometimes we might be able to find these algebraically. And this is kind of interesting because if we look at the graph of this function, you actually have a hole at x is equal to 5. So 5 is not actually part of the domain of this function. But again, this will be in another series of videos. We're going to take a couple more looks at finding the limit from a graph before we get into the algebraic approach.